So we're now ready to start talking about the limit laws. So we've spent 2 sections talking about what calculus is all about, why calculus came to be, what problems it solved, and then talking about the intuitive definition of the limit. We now want to talk about the algebraic definition of the limit, where we talk about how we actually evaluate limits. So this is a super important section. You want to triple star this one. This is going to be one of the most important sections that we cover on limits. So it's very, very important. All right. So we're going to cover what are called the limit laws, and there are quite a few of them. These are things that you're eventually going to have to commit to memory and to just knowing like the back of your hand. You've got to know them instantly, and there can be no doubt. You can't be sitting there going, what does this mean again? No, it's got to be fast and it's got to be immediate. Okay, so the limit of an identity function, we just talked about this at the end of the previous section, which is the identity function y equal x. These are the points a. So what you put in is what you get out. And the limit of the identity function as x approaches a is, of course, a. In other words, these two values right here are forming this ordered pair a comma a. The identity function is defined everywhere, right? Remember what it looks like. It's basically the line at a slope of 45 degrees that bisects quadrants 1 and 3. It's defined for all real numbers, so the limit value exists at all values. A constant function, on the other hand, is a horizontal line. There are infinitely many different constant functions, and the limit of a constant is the constant itself. So when we're writing down something like this, it may look like, what's the limit as x approaches 2 of 5? And the answer is 5. What does that mean? Well, that means that somewhere on the graph at 5, we have a horizontal line. All right. And this is the line y equal 5. And when we get close to the value of 2 from the left and from the right, it looks like it hits 5. And by George, it does hit 5. Right. So that is the function value there at 2. So the limit of a constant is the constant. So the limit as x approaches 2 of a constant function 5 means that you've got this constant horizontal line. And so the y value is that value. It is 5. All right. These are our first 2 limit laws, but we have quite a few more. If you look over here on the side, you'll see that we've got the sum law, the difference law, constant multiple, product law, quotient law, power law, and root law. So we've got a lot of laws to go through. Most of them are what you think they would be, so it's not difficult to learn them and memorize them. They're what you would think they would be based on the graphs. So here are the first ones. We're going to go through the sum law, difference law, and constant multiple factor laws quickly because they're straightforward. The product law and the quotient law are not. These are the 2 that are counterintuitive. They are not what you think they would be. And we'll talk about why they're not. All right. So the sum law just says if I have a function f of x and another function g of x, and I'm adding them together, then the limit of the sum is the sum of the 2 limits if I split them apart. So one way of writing this is the limit of a sum is the sum of the limits. Now, what does that let me do? That lets me do something like this, where I have the limit as x approaches, not equals, x approaches 1 of x plus 3, right? X plus 3 is a line, but I can also think of it as 2 functions added together. I can think of it as the function f of x equal to x, the identity function, and g of x equal to 3, a constant function. Does everybody see that? So in this sense, f of x equals x, which is the identity function, and g of x is equal to 3, which is a constant function. And this says I can split it into two limits as x approaches 1 of the identity function plus the limit as x approaches 1 of the constant function. Well, I know what the limit of the identity function is. It's the same value that x is getting close to, because what you put in is what you get out. So this would give me a 1. And the limit of a constant function is the constant. So the limit of the constant is the constant. So I get out a 3. And this says the value then becomes 4. So I'm able to split it up. Now, on a practical everyday basis, we don't actually do this. We don't actually split it up. We do it in our heads, all right? Because I know what x plus 3 looks like. If we come out here to the graph, I'm going to turn that one off. If I put on x plus 3 and I'm getting close to 1, 1 is over here, right there at 4, all right? So as I'm getting close to 1 from both sides, it looks like it's going to hit 4, and it does hit 4. So it shouldn't be a surprise that the value here comes out to be 4, all right? The same thing is true for a difference. In fact, addition and subtraction are flip sides of the same coin. There's really only addition and addition of a negative. There's no such thing as subtraction. That's a misnomer, right? There really is no such thing as subtraction. There's addition and addition of a negative, which basically is what we define subtraction to be. So when I have subtraction inside what's the limit's being taken of, I can split it into the limit of the differences, or the difference of the limits, all right? The next one is going to let me deal with constant multiples. If I have a multiple times something, then I can factor the constant off. So let's take a look at a constant multiple. Let's suppose I have the limit as x approaches 2 of 5x. The 5 is a constant, and it says you can factor the constant out of the limit and then take the limit as x approaches 2 of just the identity function x, which should give me 5 times 2, which would come out to be 10. All right, so we're doing these algebraically, not by looking at the graph and not by creating a table. So we're evaluating them algebraically. Basically, what I'm doing is I'm substituting the value in, and if I get a number, I'm like, yay, I'm done. And guess what? That's the rule. All right. The rule for the first 3 is substitute a in. If you get a finite real number, that's the limit. That's all you have to do. All right. Now, the product and quotient laws are a little tricky. This is the one thing that you're allowed to do. These two right here, you can do with limits, but with nothing else. You can't do this with derivatives, which we'll learn in chapter 3, or integrals, which we'll learn in chapter 5. There are 3 major topics in calculus. There's the limit, the derivative, and the integral. All right? The derivative is at its basic form a limit. An integral at its basic form is either a limit or a derivative, and a derivative is a limit. So the limit is the basic construct. We have more power with limits, more freedom to do things with limits than we have with any other construct. We're allowed to split up multiplication and division when we have limits, but we are not allowed to split up multiplication and division when we have derivatives and integrals, as you'll learn. The rules for those are very difficult, much, much more difficult. In fact, we spend an entire chapter in Calculus 2, learning how to deal with division and multiplication when we have integrals, all right? An entire chapter of techniques, right? Because they're so complicated, right? But with the limit, the idea is super easy. The limit of a product is the product of the limits. Which means if I have the limit as x approaches 2 of x plus 2 times x minus 4, I can split this into the limit as x approaches 2 of x plus 2 times the limit as x approaches 2 of x minus 4. Right? I can split it.
Question in that one. Can you open like so from a multiplication and then you do those
Could you multiply it first and then do it? Yes, you can.
yeah, or do the sum law like
and then
like
do the
to
sum law.
simplify it. Yeah,
Yes.
Okay, great.
Yes, you can. There's multiple ways to approach these. There's not one right answer, but this ability to split the limit of a product becomes super important later on in Calculus 2 when we're talking about improper integrals. It is what allows us to evaluate those. And we have the same rule for the limit of a quotient. The limit of a quotient is the quotient of the limits, provided, what is the one rule with division that we can never, ever violate? Thou shalt not what?
Divide by 0.
Yeah. If you come out of this class not saying thou shalt not divide by 0, I have not done my job. Thou shalt not divide by 0. All right. That is the cardinal rule in mathematics. Why? Because we made 10 assumptions to start all of math off. And one of the 10 was thou shalt not divide by 0. Therefore, it's not defined. We said we wouldn't do it, so we can't do it. We can't violate one of our own rules. All right. Okay. What about the power law? The power law and the root law are also things that we can do with limits that we cannot do with the derivative and we cannot do with the integral. In fact, the only two things that we can do with the derivative and integral that we can do with the limit are the sum and the difference rule and the constant multiple. So I guess 3 things. The first 3. We have the sum rule, the difference rule, and the constant multiple rule. We can do those with derivatives and integrals as well. And that's it. But the limit has a lot more properties that it's allowed to do. And one of them is, well, what if I have a power on this? So let me do a limit as x approaches 2 of x plus 2 to the 3rd. All right. What does this mean? Well, this means what I can do is I can take the limit of what's being raised to the 3rd power first using the sum rule and then raise the result to the 3rd power. Now, this is pretty crazy. I mean, I should be looking at the function x plus 2 quantity cubed. So we'll come over here and we'll graph that. All right, looks like that. I should be looking at that graph, but this says, no, I can look at the line x plus 2. I can take the limit of it using the sum rule, and that will give me a 4. And then I can take the 4 and raise it to the 3rd power, and that will give me 64, which is crazy. Why does looking at the line give me what I get on the cubic? It's just the power of the limit. The limit is allowed to go inside of a power, which is why it's allowed to go inside of a root, because what is another way to write the nth radical? Who remembers? I'll have to make up something. I have no idea what I'm doing. I'm making up one. What's another way of writing the square root of x plus 5? Do you remember this from your college algebra? The square root is actually the 1/2 power. So of course you can pull a radical inside of a root, because really you can pull the radical inside of the power, all right? And that's what we're doing, all right? So we can pull it under the radical, we can pull it anywhere we want to go. All right. Now let's see what else. Oh, well, let's go ahead and evaluate this one. So this would tell me that I could do the limit as x approaches 4 first of the line x plus 5, and then raise it to the 1/2 power or put it under the radical, which is the same as doing, I'll put it under the radical this time, the limit as x approaches 4 of x plus the limit as x approaches 4 of 5, which would give me the square root of 4 plus 5, which is the square root of 9, which is 3. All right, so I would get a 3. I cannot emphasize enough how incredibly powerful the limit construct is. It took hundreds of years for Western civilization to come up with the concept of the limit. And even though civilizations like China and the Aztecs and the Mayans and some of the ancestors in the Indus Valley, even though they had a rudimentary form of calculus, none of them quite came up with the idea of the limit. The limit is unique to Western civilization, and it's what created the leaps forward in science, engineering, medicine, etc. It's what created the Industrial Revolution and led to the world as we know it today. The limit is super powerful. You can split up sums, differences, constant multiples, products, quotients, powers, roots. You can do anything with a limit. You're not limited by the limit. The limit can do anything. All right, let's take a look at a couple of examples. I do also have raising to a power and a root at the same time. That's what this last rule is right here. And it has all sorts of different restrictions on the side. And the restrictions on the side come about because of two things. One, we want to make sure that what's under the radical is positive if m is an even root, right? So if we're looking at something being raised to the n over m power, so let's take x plus 2 and we'll just raise it to the 4/5 power. Just to remind you that this means the 5th root of x plus 2 to the 4th, or the 5th root of x plus 2 and then raised to the 4th. All right. So the denominator power is the root and the numerator power is a power like it normally is. When the denominator power is odd, then it's not a problem. What's under the radical could be positive or negative. We don't have to worry about it. But if it's even, then we need what's under the radical to be positive so that when we take the even root of it, we get a positive number and not an imaginary number. So we have to worry about that. The other thing we have to worry about is what if n over m is negative? Well, if you have a negative power, what would it mean to take x minus 3, to the 2/3 power that's negative? Well, that would be 1 over the cube root of x minus 3 squared. remember that when the power is negative, it drops it to the denominator. So when we drop it to the denominator, if it's negative, which you see right here, n over m is negative, then we have to make sure that what answer we get isn't 0, because thou shalt not what? You had better not divide by 0. All right. Thou shalt not divide by 0. Full stop. And that includes if the power is negative and it drops it to the denominator, thou shalt not divide by 0. So we've got to watch out for that as well. So there are all kinds of tricky little things you have to watch out for. It's easier with actual numbers in there to tell whether or not it's something you have to worry about. So you could have something like x plus 7 to the 7/4 power. And then I do have to worry about this, right? Because I've got a 4th root and an x plus 7, and then it's going to be raised to the 7th power. I have to make sure that this is not negative. All right. If that's even, then it can't be negative. And that's why you have this L greater than or equal to 0 here, not negative. That's what this means. If n over m is negative, that puts it in the denominator. So then it has to be not negative and not 0. And that's what the last restriction is. Okay. Let's use limit laws in order to evaluate. So I've given you all the limit laws. And what we're going to do is we're going to apply the limit laws one step at a time. Now, I will tell you right now that this is not the way we actually do it. So we're going to do it straightforward by applying the rules one step at a time. And then we're going to redo the problem the way we'll actually do it in practice. So the first thing that I see that I need to break apart is this multiplication right there between the two factors, 2x minus 1 and the radical x plus 4. So I'm going to split those two apart. So this is going to give me the limit as x approaches 6 of 2x minus 1 times the limit as x approaches 6 of the square root of x plus 4. And this is the product law. All right. Then I'm going to split up the first one using the difference law. So this is going to let me write x approaches 6 of 2x minus the limit as x approaches 6 of 1. And this is the difference law. And on the right side, I'm going to take the square root to the outside and put the limit underneath it. And this is the root law. Does everybody see? I'm applying them one step at a time. All right, justifying it each step. The next thing I'm going to do to the first limit in the left factor is I'm going to factor out the 2, and that's going to be the constant factor law. And then over here, I'm going to split these two using the sum law. So I have the limit as x approaches 6 of x plus the limit as x approaches 6 of 4. And that's the sum law. And now that I've reduced pretty much everything inside of the limit to one single factor, one single term, now I can go ahead and evaluate it. So this is going to give me 2 times 6 minus 1 for the first set, the radical of 6 plus 4 for the second set. 2 times 6, remember, order of operations, multiply first. So I get 12 minus 1. And the second set, I get the square root of 10. Don't do the square root of 6 plus the square root of 4. That's false. That does not work. And that's 11 square roots of 10. All right, and that's the way that you would apply it, by splitting it up one step at a time. Now, I said I would redo it the way we actually do it. All right, so how would we actually do it? If I were really going to do this, what is the way that I would actually do it? If I were actually going to evaluate the limit, I would start at the beginning and I would plug in the value of 6. If I get a finite real number, I'm done. That's really what I do. Okay, let's take a look at the next one, which is the same example. Use the limit law. So we're going to justify each step. We're going to split it up one step at a time, and then we'll do it all together in one fell swoop. So the first thing we're going to do is we're going to split it according to the quotient. So we're doing the reverse of the order of operations. We're doing the last thing, it's the first thing we split up. And this is the quotient rule. Or quotient law. Right? Which says that the limit of a quotient is the quotient of the limits. And then I can use the sum law for the top. And the difference law for the bottom. And then what laws should I apply? What would come next? There's a couple more I need to apply. What two do I need to apply now?
Power law.
Power law. So that would be the first one. So I'm going to do the limit as x approaches 1 of x raised to the third. This is the power law. Plus, I'm going to pull the 3 out. This is the constant factor law. And I'm going to raise this to the power. So I'm going to have the limit as x approaches 1 of x raised to the power 2. That's the power law. So I applied 2 laws there, the constant factor law and the power law, plus the limit as x approaches 1 of 5, all divided by the limit as x approaches 1 of 4. There's only one thing there, so not much to do. And then the constant factor law in the denominator. And then the next thing I'm going to do is evaluate each one of them individually. So the limit of as x goes to 1 of x is 1. So this gives me 1, then raised to the power 3, plus 3 times the limit as x goes to 1 of x is 1, raised to the power 2, then multiplied by 3. The limit of a constant is the constant. The limit of a constant is the constant. Then I've got minus 7 times the limit as x goes to 1 of the identity function. So that's going to be a 1. And that's going to give me 1 plus 3 plus 5 over 4 minus 7 which is going to be 9 over -3, which is -3. All right. And that's how we would apply it if we were doing it one step at a time. That's not the way that we would actually apply it. What's the way we would actually apply it? If we were actually doing it on a test or a quiz, what would you do?
Substitute the, it's approaching 1, x is approaching 1, so substitute 1.
Yes, so substitute 1 in and see if we get a finite real number. If we get a finite real number, it worked and we don't have to do anything else. So I do 1 cubed plus 3 times 1 squared plus 5 over 4 minus 7 times 1, which would still give me the 1 plus 3 plus 5 over 4 minus 7, which is still going to give me my -3. Right? And is much, much shorter. Okay. Let's take a look at the limits of polynomial and rational functions. The limits of a polynomial function, this is what we've been doing when I said this is the way we actually do it. If we have a polynomial, we plug in what the x value is approaching and the limit is p of a. So this is what we used just a second ago when we said the limit as x approaches 1 of this rational function. We take the 1 and we plug it into the polynomial in the numerator and we get these values. We take the 1, we plug it into the polynomial in the denominator and we get these values. That's all it says. Plug in the value that x is approaching and see if you get a finite real number. All right. Now, we're not going to go through the proof because I've only got about 15 minutes left. So I don't want to take the time to go through the proof, but the proof is right here. And it's pretty straightforward. It just uses the limit by applying the sum and constant multiple and power laws. And you get that the limit of p of x is p of a. All right. So let's practice this a little bit. So looking at this, we have the limit as x approaches -2 of a polynomial 3x cubed minus 2x plus 7. By the way, who can define a polynomial for me? I mean, I'm throwing the word around like you know what it means. Do you know what it means?
Does it have to do with the multiple exponents on a variable?
It does have something to do with exponents on the variable. What can the exponents on the variable be?
N minus 1 or yeah, all of that.
Ah, whole. Oh my, what happened there? Okay. Whole number exponents. What's a whole number?
No fractions or decimals.
No fractions, decimals, radicals, or roots. In other words, 0, 1, 2, 3, 4, 5, etc. No negatives either. All right. So no x in the denominator. And what's the second requirement to be a polynomial? It has to do with the coefficients. What kinds of numbers can you have as coefficients?
Rational?
More than rational. It's allowed to have pi as a coefficient. Just real. Just real. You can't have I. I am going to ask this on the first exam. I'm going to ask you what 2 conditions are required to be a polynomial. And you're going to say whole number exponents on the variable 0, 1, 2, 3, and 4, and real coefficients.
So when you write the designator for real numbers there, how do you read that, or how does, I don't understand.
Real coefficients, the double bar R, is that what you're asking?
Yeah, where does that come from?
Double bar R means real. Double bar N is natural numbers. That would be the counting numbers, 1, 2, 3, 4, and so on. There's a double bar Q, which looks really weird. This is rational numbers. All fractions. And there's a double bar Z, which is integers. These are just math notation. They're shortcuts for writing these different classes of numbers because we have to write them so often. So the double bar R stands for all reals, double bar N stands for natural numbers, double bar Q is the rationals, double bar Z is the integers. I don't know why Z is integers. I know Q stands for quotient, which makes sense. You've got rational numbers, which can be written as the ratio of two integers. But I'm not sure where integers got to be a Z. But that's what they are. Okay, let's take a look then at this example. We have the limit as x approaches -2 of 3x cubed minus 2x plus 7. The coefficients are 3, -2 and 7. Those are real. The powers on x are 3, 1, and 0, because the last one could be written as 7x to the 0. So those are whole numbers. So it is a polynomial. So we just plug it in. So this becomes 3 times -2 cubed minus 2 times -2 plus 7. And then we evaluate. Powers come before multiplication. Be very careful. This becomes a -8 before you multiply by 3. This becomes +4 plus 7. This is -24 plus 11, which is what, -13? You guys verify. Check my arithmetic. All right. All right. Roz is nodding her head. So I feel a little confident I did that one right. All right. Now, the next one, what does that mean? That means as you trace along the graph of that rational or polynomial function, as x approaches -2, the y value goes to -13. That's what it means. Let's graph it so that you see it. Somebody tell me what it was. It was 3x cubed, then what?
Plus, minus 2x plus 7.
Okay. There it is, right there. And as we get close to -2, it's supposed to get close to -13. So here's -2 coming down this line. So let me put x equal -2 on there. And I'm going to dash it since it's not actually part of it. And we're going to look where it crosses, which is right there, bingo, at -13. As it approaches -2, the y value is 13. That's what the limit means. That's the connection between the intuitive idea and the algebraic. All right. Let's look at the next one, which is the limit as x approaches 0 over 1 divided by 1 plus sine of x. This is not a polynomial, but we're going to treat it the same and we're going to plug in. If we get a real value, we're done. If we get division by 0, we'll have to do something else. And that's what we're going to be looking at tomorrow. All right. Tomorrow, we're going to be looking at what happens if you get division by 0. And it depends on whether you get 0 over 0 or just 0. And we'll probably see some of those today as well. So we have the limit as x approaches 0. So we're just going to plug in 1 over 1 plus the sine of 0. From your trig, which you've all just had, what is the sine of 0? 0. So 1 plus 1 gives us 1. That means that when we look at the graph of 1 plus or 1 over 1 plus sine x, and we get close to 0, the value should be 1. And there it is right there. As we approach the graph from both the left and the right side of 0, the y value looks like it hits 1. And in fact, it does hit 1. It is defined there. All right. That's what the limit is, the intuitive and the algebraic. Let's do it again. The limit of 2 minus 7x over x plus 6, we're going to plug in the value. If we get a finite real number, we're done. And we get 2 minus 7 over 7, which is negative 5 over 7, right? And again, if we go to the graph, that means that as we trace along the graph and we get close to 1, the y value is going to be negative 5/7. Now we have some more algebraic techniques that we want to talk about. And some of these are going to be what happens when you get 0 over 0 when you try to plug in. These are some ways that we try to counteract that. All right, so we have a variety of techniques that we use to deal with 0 divided by 0. It's an indeterminate form. It does not exist. It means the function is not defined there because thou shalt not divide by 0, full stop. Thou shalt not do that. But that doesn't mean the limit doesn't exist. The limit may still exist, but the function doesn't exist there. But we could have a hole in the graph. So that's what we're looking to see, is whether or not it's a hole in the graph. So when we get 0 over 0, we have a variety of techniques. One of the things we can do is cancel like factors. So for example, if we had a function and we have the limit as x approaches 3 of x squared minus 9 over x minus 3, this actually, if we were to factor it, wouldn't this be x minus 3, x plus 3 over x minus 3? And what would happen with the x minus 3s? They would cancel, and we would still have x plus 3. But because they were there in the beginning, this would lead to a 0 over 0 result. But if we cancel them and then we do the limit, then we would get 3 plus 3, which would give us 6. The y value would be at 6, which means there's a hole in the graph and it looks like it's going to hit 6, but in fact, it's just a hole. All right. So these are the graphs of x squared minus 1 over x minus 1. And again, if you look at x squared minus 1, you can think of x squared minus 1 over x minus 1. You can think of this as x minus 1, x plus 1 over x minus 1. The two cancel, but because it was there in the original function, thou shalt not divide by 0, you cannot allow x to be 1, because that makes the original one 0 over 0, which is undefined. So we make a hole in the graph, but the hole becomes at this value, which would be 1 plus 1, which is at 2. So we have a hole in the graph at 1, 2. So let's look at another example of this one, which is x squared plus 4x plus 3 over x squared minus 9. How do we even know we need to do that? The first thing we always do is just plug it in. So we're going to plug it in. So we get negative 3 squared plus 4 times negative 3 plus 3 over negative 3 squared minus 9. This gives me 9 minus 12 plus 3 over 9 minus 9, which gives me 0 over 0. Did not work. That didn't work. We plugged it in, but thou shalt not divide by 0. We got 0 over 0. But because it's 0 over 0 and not a constant over 0, like 5 over 0, I know it could factor. So I try again. And I'm going to try to factor. Why factor? Because it's a polynomial divided by a polynomial. And when I see polynomials, I just have this knee-jerk response that I need to factor them, basically. All right. So I'm going to factor. I haven't done the limit yet because I had to back up. That didn't work. I got something undefined. When I factor x squared plus 4x plus 3, I get x plus 3, x plus 1, which gives me 3x plus 1x or 4x in the middle. And when I factor x squared minus 9, I get x plus 3, x minus 3. Does everybody see where that 0 over 0 result came from? X is approaching -3, and when I plug that into x plus 3, it causes each one of these to become 0. That's where my 0 over 0 came from. But I have the same factor in the numerator as in the denominator. So even though the function's not defined, the limit may be. So I'm going to cancel this factor, and then I'm going to plug it in again. So now I get -3 plus 1 over -3 minus 3, which is -2 over -6, which is a positive 1/3. Right. Now let's take a look at what that looks like over here. All right. So the question is, what happens as I approach -3? -3 is out here. Now remember, Desmos is not good at drawing holes unless you click on the spot. So my -3 is right out here. So in order to see it, I've got to move the cursor and click right on it, which I can't do that and face backwards at the same time. There it is. And what is it telling you happens at -3? What does it actually say? Undefined. So what it actually means is there's a hole in the graph right there. It's not defined there because thou shalt not divide by 0, but the limit exists. And the limit is that value, which is about 1/3. And you can tell it is at a height of about 1/3.